Good evening. Today is our last class before exam 2. What? The midterm exam? I mean, there's 4 equally weighted exams. The last one is, the last exam is cumulative. The other ones are semi-cumulative. So the material on this exam will be between the, go ahead, Cassandra. Everything from exam 1. So exam 1 we kind of ended on like, look at the periodic table, figure out how many valence electrons something has. Right? That's where we stopped, based on quantum. So everything from that point forward that we've done in class, that's what you need to be able to do for exam 2. The logistics-wise, there are still some people who haven't passed the plagiarism test or posted that. If you have not done that, you cannot, like it's a departmental policy. You have to do that or else you don't pass the class. So find someone else in this class. If you are one of the people who has not passed that, there's about 10 people. Talk to the person sitting next to you today. Say, hey, do you mind staying for like 2 minutes after class while I pull that up and talk through the questions with me and see if I'm missing something?
I'm really good at it.
He's really good at it.
Find John Paul. Okay. So the idea is that you should do it within the first week of the semester so that we know what plagiarism is. We don't copy other people's work. We don't take credit for other people's work. If you haven't been able to get through it, there's some technical details. John Paul will help you out with those, so make sure to see him in the polo shirt up front. Okay, so please do that. I did post all of the grades that I have available on Friday afternoon. So that means that your lab grade up through experiment 3, including workshop through experiment 6, all should be completely up to date. And your mastering homework is updated and your iQuickers are updated. So what you see on Blackboard right now should be very close, if not actually what your grade is at this moment in time. Remember, the exam replacement policy exists. If you didn't do as well as you wanted on exam 1, make sure you show me by the final exam you know how to do that and get a higher score on the final than your lowest exam. And that means that you will get rid of that lowest exam score and your final will count twice. So it doesn't mean you're locked into the score you see now, but that is where you are right now. Okay? Questions? Okay, I have office hours tomorrow, 10:30 to noon, and Wednesday, 3:30 to 5. If you cannot make either of those, and you really want to meet and chat about a topic or a concept, send me an email. I can try to be flexible with my timing and meet up with you. There are also the tutoring center and math assistance center, and your peers maybe form some study groups is valuable if you want. Jay, you have a question? 10:30 to 12, and both of those are in ETAS 125, which is the corner of this building right behind us. It's a bigger space. So bring questions, we'll work through problems, it'll be an interactive review session, study session. I will not come with specific questions, but if you say, I want to work on this topic because I don't get this, then I'll make up some questions, we'll work through it, and we'll make sure you're comfortable with it. Okay? All right, so we have a lot to do tonight. The reason is because 1, I want to get you ready for the exam, and 2, I want to get you ready for lab this week. So we're going to do both. And some of the stuff that we're going to do tonight, that I think everything we're going to do tonight actually will be on the exam as well. So let's make sure that we're confident we're moving forward succinctly. That means that if you get stuck, if you're like, I don't even know how to start this, what do? Raise your hand, make sure that one of us will come around and help out. We have a lot of people here in class tonight, once again. We don't want anyone just sitting there idle. Ask the people around you. If that doesn't work, call one of us over. Let's keep moving. All right, so we have our first question up here. We have a little bit of a mix in answers. We have 44 responses. Seems like we have more people than that here. Let's have someone describe the process of how we answer this question. 1, we'd have to know that this is a salt. That is a little bit of a piece of information that's left out. I'd have to say, this is a salt, and this is the formula. So what do we know about X? How do we answer that question? Can I hear the process? Volunteers. Eleanor?
Okay, so we know that X is a cation, so it's positive.
Why is X a cation? Why do we know that?
Because it's the most electronegative
But we don't know anything about it. How do we know it's...
Because X represents something. It's representing a hypothetical cation.
It is. How do we know it's a cation?
Oh.
I completely agree, but what is it that's telling us that that's a cation?
What is it that's telling us?
Tara?
The F is -1, so it would be -3 because there are 3.
Whoa, so you're going way past where we wanted to go. I just said, how do we know that X is positive? And so the reason we know X is positive is two ways. The first part of a salt is always the positive. It's always a cation. Okay? The second reason we know is because F is, if it's an ion, is...
So F is the anion, and it's negatively charged.
Negative how many?
Well, it would be -1 because there's nothing, because we're going to do the switchy.
No, don't do the switchy.
No, we don't do this. Okay. F is -1, and then X would be +3, and so they're charged. And then we know we do the switchy.
We don't do the switchy.
We don't do the switchy.
I hate the switchy.
What?
Because the switchy will end up where a lot of people, if it was like a -2 and a +3, then they'll end up with 6 for both. You can mess it up. So let's recap. In order to figure out what the charge on X is, we know it has to be positively charged for two reasons. Because one, it's first.
It's a cation.
Two, it's paired with something that we know is always, if it's in a salt, it's going to gain 1 electron, because that's all it needs to have a noble gas electron configuration. Okay? So it's going to have fluoride, it's going to have a -1, we call it fluoride. And then we know that we have 3 of them, so instead of writing 3 times -1, I wrote -1, -1, -1, just so we're thinking about each of the fluorines having its own -1, and there's 3 of them. So that means that our X is going to have a +3. So if I said, could this be in group 2? Could X be a metal in group 2? What do you think? Talk to your neighbor. Could X be a metal in group 2? What do we think? Put your thumbs up. Yes, it could be a metal in group 2. Down, no way it could be a metal in group 2. Why? Summer, you look pretty adamant about that. Why did you say no? Do you want to share your thoughts? Okay. Morgan, would you like to share? Dustin, I'm going to go along the row.
I would. The reason why it can't be in group 2 is because normally elements in group 2 have a +2 charge.
And I would even modify that, not normally, always.
Always.
If we find a metal in group 2, it will either be neutral, all of its electrons, or if it's in an ionic compound, it will have a +2 charge. So that X could not be from group 2. It would have to be a transition metal or one of the special ones, so silver, Ag is always +3, and it could be that. Okay. How are we feeling about working with salts? We'll work with them a little bit more to give you some more confidence here in a second. So I want you, are we out of worksheets? What are you stealing them for?
I don't have one either.
Monica, you're rubbing off.
It's interesting.
All right.
You said that silver always has a charge of +3, or I thought that was 3, 2, 1, and not 1.
Oh, sorry. I am wrong. So aluminum always has a +3. Thank you, Chris. Zinc has a +2. Silver has a +1. I said that backwards. Fail. Jade? Or Jocelyn, sorry. There is one extra floating around here. Where did that extra go? Someone have an extra?
I don't have one either.
Why do we... Okay. You guys can share. You can share this between the two of you. It's single-sided. Thought I printed out enough. This is strange. Okay, sorry. If you don't have a worksheet, make sure to sit next to someone that does, and then try to work together. I think it is posted in Blackboard, so if you have a tablet that you want to use it on, you can pull out your tablet, go Blackboard content. It's listed there under week 8, 7.
I can do that if anyone wants this one.
Okay. So today, by the end of the day today, we have a big list of things I want you to be able to do. One is we're going to talk about determining if a salt is water soluble, something you've done in lab. We're going to build off of that. We're going to talk about differentiating between liquid and aqueous. Those are two terms that have been thrown around in lab as well that I want to build off of for class. We're going to balance chemical reaction. We're going to do that both mathematically, thinking about numbers, but also using sentences to describe what that actually means. And then we're going to talk about, these are mostly lab-specific things for the second half, but they will also be, they're important for both. Calculating the molar mass of a compound. We've talked about molecular weight, maybe. So molar mass is kind of building off of that. And then use that molar mass to convert between weight and quantity to weight, kind of going both directions. That's where we're going. Big list, right? Kisa, quick question? What makes something a salt? Having a positively charged part and a negatively charged part. So cation and anion together. So kind of these are the last couple questions on our worksheet from last Wednesday. I asked you to determine what the name of this compound is. So go ahead and submit your response. Pull out your worksheet from last class if you don't have it. And we're going to try to go through these relatively quickly. Hopefully you took a look at them after class. Say again? I think so. Can you find it?
Yeah, it's week 8 because we start term 5 tomorrow.
No tablets today, right? Because I don't usually give you. All right, so hopefully you all have your worksheet from last week. Was it the second? These are the questions towards the bottom of the backside. Talk to your name, try to answer it. What is the name of this compound?
I was thinking the whole time. Because I think C is correct because there's no sulfide.
All right, looks like we have 46 responses. We're not in agreement. Turn and find someone with a different answer than you. Convince them you're right.
Because that would be 6 charges.
Iron can be 2 or 3. Yeah.
So that whole thing is each SO3 has a charge of minus.
So looking at my little cheater down here, we did have a couple discussions, but about 15 people did not talk to someone that convinced them otherwise. Come on, you got benefits all around you, people that can help convince you. So why is the right answer D?
Is what? What's not?
Someone like to argue me. Is the right answer not D? Why is it not D? Let's go ahead, Jay. Why is the right answer not D?
Okay, so on this sheet, let's apply this on the ion. Sulfite is SO3 -2. Sulfate is SO4 -2. So first of all, it's not no 2 right beside the S anyway, so that can't be it. Then sulfide can't be correct, because that's like a 1. So anything in with a sulfide not right. So it's on the only.
So wait. What is sulfide?
It's one.
What is sulfide?
Oh, it's like
It's S by itself with what charge? If we found sulfur as an ion, what charge would sulfur have?
Minus 2.
It's not bound to an oxygen.
it needs.
So if sulfur, the way that we need to look at the periodic table, so this is why I hate that stupid sheet that you're all looking at. Put that sheet away.
Which one? I like
What about the charges and the names? So one, there's literally 2 days until I'm testing you on knowing the names, so put those sheets away and test yourself. 2, the periodic table, the brief version with all the charges, put that away.
How are we supposed to do it?
What I want you to do with the charges is to say, if we found this group 8 in nature, would we find it as an ion? And if so, what charge would it have?
It wouldn't be an ion.
This group on the far right would never be found as an ion because they're double gases. That's electron configuration, everything it's trying to attain. What about group 7? Main group 7. Negative 1, because if they gain 1 electron, they have the electron configuration of noble gas. Group 6. 2 electrons, or if they form a bond, if it's a covalent bond, it's going to be sharing 2 electrons or having 2 bonds. Right, so sulfur is here. So if sulfur, we put "ide" on the end, that means it's a negative charge. So sulfide, can't write on that screen, just means sulfur with a 2 minus. That can be an anion by itself. That's what sulfide means. But we have SO3. How do we know the charge of that?
Polyatomic.
Because we know the language of chemistry, sulfite is SO3 2 minus. Okay? That then dictates what the charge of the cation is, because the cation is a transition metal. So it could be +2, +3, +5, +7. Iron can do a lot of different things. So what's the charge of iron? How do we figure that out?
You're supposed to do it in the Roman numeral.
So we don't have it here and then figure out what it is there, right? We figure out this and then we write the Roman numeral as the name. So how did we figure out whether it was, I didn't even give you the option, right? So how do we know it's iron 3? Chris, how'd you figure it out?
Because the salt needs to be neutral, so if we have the charge of 2 minus on the SO3 and we have 3 of them, that gives it a total charge of 6 minus. That means if we have 2 iron, then both of them need to be 3 plus.
Great. Questions on that? So what Chris really nicely said is that we know, because we've memorized our polyatomic ions, that SO3, each one of them has a 2 minus, and we have 3 of them. That's -6. But the salt is neutral. There's no overall charge, so that means we have to have 6 positives in there as well. How do we get 6 positives? Well, we have a cation. What does each one of them have to be charged to give us a total of +6? 3. So that means that each of the irons is a +3, and we describe that with a Roman numeral 3 because it's a transition metal. So Jay was right, and she was correctly adamant that I was wrong. Thank you. All right, next question, important question. Is it soluble? Is iron 3 sulfite soluble? Yes or no? Do you have anything from lab that would help?
Yeah.
Maybe something that looks like this? And actually what's kind of funny is that you can't even answer it with this.
Yeah, because we have iron 3.
Not bad.
No iron 3 feels bad.
Okay, so if it was iron 2, would you be able to answer this question?
Yeah.
How? How would we use this table to answer this question? Can I get a new person to show us here? Carmen?
Okay, all right. I'll do my best.
So I want to know how we'd use this table to figure out the solubility if we had iron 2 ions and sulfite ions.
So I would like, y'all can't see my finger, but I'm going across the top.
So you can draw.
Okay,
Draw lines.
so go across the top, find iron, and then you said sulfite.
Yep.
Don't judge me. I'm gonna pick one of these now. I might be wrong. Don't y'all start yelling at me. Okay.
And then what do? So you have two circles. Now what?
Compare them.
What do you mean?
Where you can look. Well, hold on. Where you can look down at the gray area.
Does anyone want to help add to what she's doing? Pass it on.
I was not there that day. I don't know how to use that.
Okay. So we have our two ions identified, and then the table is very useful because we look at where
Oh man, it drew a question. Sorry, y'all.
those two intersect on the table. And if it's dark, it means it's insoluble. What does that mean? What does insoluble mean? So think about putting a block of marble into a glass of water. Is that soluble or insoluble? Insoluble. What if we took limestone? You know what limestone is? If we put that in water, what's going to happen? Calcium carbonate. Limestone. So you can see that's not very solid. What about table salt, sodium chloride? Sodium chloride dissolves. All right, so that's kind of how we use this table. So we're going to use this. Do you want to take a screenshot if you don't have your version with you? Or take a picture because I'm going to ask a few more questions about this. If I ask any questions about solubility, I will give you that table. So you need to know how to use this table. All right, a couple more seconds if anyone wants to take a picture. I guess you have no, you don't have the screenshot from Sapling. So here's my philosophy on memorizing things. If I didn't memorize them and I have a PhD in chemistry, I'm not going to make you all memorize them. This I did not memorize. But with that said, I have the trends, the basic trends. So what are the trends that we see from this table? So these two columns are always soluble. Where are those two columns on the periodic table?
First two,
Group 1. So group 1 are almost always soluble when they're a salt. What about across the top? Which ones are always soluble? Acetate, chlorate, perchlorate, nitrate, chloride, bromide, iodide are almost always soluble, and then some of these are much less soluble. So those are like, there's these rules that are written out, maybe you've seen them in the book, it's like, if this, then that, and it's like a super pain to try to memorize. But if you can look at this, and you see on the exam, oh, I have a nitrate, I know it's going to be soluble. Don't even need to look at the table, right? Nitrates are always soluble. Is that true for sulfates? Sulfates, no, there's a lot of exceptions. So it just helps kind of using this a couple times and thinking about what they look like.
What are the stars?
The stars mean that while they technically are soluble, as soon as they form, they react. And so they're usually flammable once they react. So if you have sodium oxide, it burns up in water. And so it does dissolve, it's not there afterwards, but it then does a chemical reaction. So our last one, how do we answer? All right, we got a majority of people. Let's go through another few. So let's do this compound here. What is the name of this one? We're doing those last 4 on the page. We're going to try to pick up some pace, do these last 4 pretty quick. And I'm going to ask if each one is soluble, so figure out how to answer that for each of the last. We have 3 left. We're up to 33. If you're stuck and you have no idea what you're doing, check the person next to you or wave one of us over.
The reason why he doesn't like that is because it's not complete. So, for example, iron ore exists. Yeah.
All right, we are not in agreement here on this one. Can I hear from someone in kind of the middle back section how you would solve this? Either Ada, Maddie, Caitlin, one of the three of you. Any one of you want to describe your process for answering this question? Why? Great. So we know it has to be a neutral salt. If we know our polyatomic ions, then we know the total negative charges. So then we can figure out, well, plus 4 total, and there's only one of them. So it has to be lead 4 sulfate. Okay. On an exam, I will ask you this question without giving you options. So you will need to know how to name it. You will need to know the difference between sulfite, sulfate, sulfide, nitrate, nitrite, nitride. And then you'll need to answer a question like this. Is it soluble? 15 seconds. Is lead 4 sulfate soluble? Couple more seconds. Closing out. What I want that table to do for you is to make this a really quick process to answer. So, Cassandra, how'd you answer this? Okay, so if I go back to the table, we go to lead. Do I have lead 4 on here?
No.
Why don't you tell me you can't do this? Okay. So lead 2 is not very soluble. Lead 4 is even less soluble. And you'll see that this is where it would be if it was lead 2. What do we notice about the trends? Which ones of the cation on the top and the anions on the side, which tend to be more soluble, which tend to be less soluble? Do you notice any trends about them? Megan, you have an idea? I don't know if you were raising your hand there. Okay, so that group 1 is pretty soluble. Group 8. Oh, you mean down the middle? So group 18 we don't have in salts, though. What are you thinking, Chris?
The elements that are on like the leftmost side and the rightmost side are more likely to be water soluble. Well, just more soluble in general.
Some of them, so the two extremes. So main group 1, main group 7. But what about the total charge? What happens when the charge gets bigger? Do they become more soluble or typically less soluble when the charge is bigger? So if we look at, I'll clear this out, the ones that are the most soluble for cations are the ones with the +1. Once we have higher charges over here, we tend to have most of those be less soluble. As we go down the periodic table, we start with -1s at the top. There's a couple exceptions, right? But overall, the bigger the charge, the stronger the attraction between the two. What I want us thinking about is, what does it mean to dissolve? So I think this is a question I'll get to in a second. So for now, let's do last couple. So we have 2 more compounds here. We're going to do these really quickly. All right, we have 23 in. Talk to your neighbor if you're stuck. Wave one of us down, please. How are you going to answer it? Does that help? Everything original. Why? Why is it not the second one or the third one? Big important question. We'll get to it in a second. Sorry. Okay. So if I wanted to say that this is answer D, what would you tell me? Why? Bradley, everyone's telling me I'm wrong. Why?
Because strontium is, you look on the periodic table and it's not a transition metal, so therefore you know it does not have any or multiple charges that it could be. So you know it's going to be a +2 charge.
Always a +2. So that means we don't need the Roman numerals. The simplest possible way we can write it is how we should. There should be no Roman numerals beside that. Okay, great. But then I kind of like B. Why would I like B, and why is that wrong? I see you shaking your head in the back. Do you want to explain why? Opposite way around. So all of the ones we've been looking at today are ionic. That means that it's a cation with an anion. If we do that, we do not use di, tri, tetra, anything to describe how many are paired with each other. So Keis's question before was super important. We need to first identify if it's an ionic compound. If it is an ionic compound, which is usually a metal and a non-metal, the only exception to that is the polyatomic ion. What's the name of that one? Ammonium. This is the only polyatomic ion that is positively charged with a cation. If we have a salt between a cation and an anion, we're going to use the naming structure we've done so far, and we don't use di, tri, whatever. So that we only use if we're bonding between two things that are closer in electronegativity, meaning that they are covalently bound and they are molecules, means not ionic, that they have covalent bonds holding them together. So B is also wrong. And then the rest of the class said, I know it's A. So we know it's strontium, which tells us it's a +2 charge. We know it's nitrite. Is it a neutral formula? Nitrite is -1. There's 2 of them. Total -2. There's a total +2 from the strontium. It's neutral. Can we answer if this one's soluble? Do we not have nitrite in there? I am just on fire today. I just threw in this is a soluble question for all of them. I will not do that to you on the exam. How's that sound?
But can we judge it the same way since it's group 2 as we would magnesium? Can you not do that?
The problem, so strontium is actually on that sheet. The one that is not is nitrite.
Bam.
So nitrite is not on there. Let's say, what do you think about strontium nitrate? Would that be soluble? Yeah, that one would be. Okay. So go ahead and just click on something so you have a response to that, and I'll close it out. Ready? Closing. Submit, close. Okay. What about this one here? Go ahead and click in the name, and then let me see if this one we can tell if it's soluble or not. Let's do 20 or 30 seconds on this one. All right, 10 more seconds. Closing out. So, would we use answer B or A here? I heard A and B being responded. Which one and why? Who wants to argue? Raise your hand. Shelby? Why? Okay, so I agree that this is S by itself. How do you know it's an anion? How do we know it's a salt? Fair. I could have just been sloppy in my writing and put salt. How do we know it's a salt? What are we looking for? Cation and anion. But really, it's two things that are on other sides of the periodic table. Remember, the difference in electronegativity between those two elements is so big that we would say that bond is extremely polar to the point it's ionic. So what we're talking about with salts is there are ionic bonds that is either between a known polyatomic ion or between a metal and a non-metal, typically because their differences in electronegativity is so big.
Does it look like salt? Like,
Lithium sulfide?
like
Google a
salt
picture of it.
Salt.
I imagine it would. So most of the time they're crystalline, sometimes they're clear, sometimes they're not clear, they're opaque. What about solubility of this one? Can we answer that? You could, if you think about the trends. So go ahead and answer this question when thinking about the trends. Couple more seconds. We were not as sure about this answer. How do we answer this question? We don't have lithium on there. How do we answer it?
It's group one.
Group 1. And what do we say about group 1?
They're mostly soluble.
Group 1 is almost always soluble. So you can kind of extrapolate a little bit from there because all the group 1 metals are soluble in that table. And actually, that's one of the rules, is that group 1 metals are always soluble. So we can't extrapolate, and that might be useful after class is over. And using it in real life. For the exam, I will not give you a question like that if you cannot find it on the table. You need to know how to use the table. Okay, so I'm going to talk for let's do this. Discuss with your neighbor for just 1 minute. I want everyone asking someone else beside them. What's the difference between something being a liquid versus something being aqueous? If I see you not talking to someone, I'm going to come over there and talk to you.
aqueous is dissolved in water. NaCl, salt, put in salt water, that's what it is. Because they soak in the water. You wouldn't call that liquid salt. You would just be
All right, now one very quick shout out of maybe some of the findings of your discussion. What kind of differentiates these two, liquid versus aqueous? Can I get 2 or 3 volunteers? Come on. No. Sure. Okay, so one of the major points that Mel is making is that liquid is pure and aqueous is a mixture. Does anyone want to add to that? Let's add something to that. What discussions do you have in your group? Aqueous is a mixture with water. I like that. So we're adding more specificity to it. What else? Shelby? Danielle? Emily? Sorry, I'm having a hard time hearing them. Go ahead, Shelby. What do you think? Is the only liquid possible water? No. Kalia?
No, because if you heat a solid up really hot and it gets to its melting point, it'll still be a pure substance.
So are there any other liquids that you might have seen in your daily lives? Mercury. Mercury is a metal that happens to become liquid at a very cold temperature relative. If we took aluminum and wanted to make that a liquid, we'd have to heat it up to, 1,000 degrees Fahrenheit or something. So a liquid is a state of matter. And I would say that for the purposes of this discussion, I wanted to focus on that aqueous just means that it has water and then something in it that is dissolved. You can have liquid that is a mixture, so vodka is a liquid, and that's a mixture of H2O and ethanol. But you could also say that that is an aqueous mixture because it is dissolved in water. So when we say, if we have a chemical reaction and we say liquid, that substance is a liquid, it means that that is the state of matter that substance is. So usually that is a pure substance. In everyday speak, that's when it can be a mixture. So for our class, we're going to say that the purity is one of the things we're considering. So I'm going to really briefly show a visualization of what that looks like. So if we have a whole bunch of molecules, each one of these is a molecule. Is this liquid?
No.
How do we know it's not a liquid? So it's all grouped together, it's defying gravity. There is movement, but what is the movement? It's just vibrating, right? And so they're held next to something beside them, and there's energy, you can see that by a little vibration and movement, but they're not doing what a liquid would do. What would a liquid look like if it was in this container? Gravity would pull it down, it would spread out, and what would the things just stay next to each other? The molecules would be all moving past each other. How would I make that happen? How would I turn this into a liquid? Warm it up, right? So I can go in this simulation and I can add heat. And if you notice, the movement of the molecules, it's hard to see with this view. It's kind of like a weird simulation. I actually don't know what the boiling point of this, the melting point of this is. But a lot of them are now starting to move past each other. Gravity's starting to pull them down. There's still a few that will escape. This is why puddles evaporate on a warm day. It's not because we're boiling the water outside, but some of the molecules are in a gaseous state. What's another way, if I reset that, what's another way I could make this into a liquid? So we could talk about making mixtures, but that's a little bit different. Do you notice this interaction strength bar here?
Oh,
Why are they staying together?
their bonds are ion. No.
if we have a net dipole, so let's just draw water for instance, we have a net dipole, it means there's slightly positive parts of the molecule, slightly negative, and they're not symmetric. If another water molecule comes around, its dipole is going to point towards the other. So the more electronegative part is going to be attracted to the more partially positive part. So what if we made these less attracted to each other? We decreased the attractive forces between them. They have less of a dipole. So now you can see there's less strength holding them together, and we could add heat now. Maybe we don't need to add nearly as much heat. Just add a little bit of heat. And it changes the overall shape of the substance. It changes the state. So all that stuff we've been talking about dipoles and do they have a dipole or do they not, if they have a net dipole, it means that they're going to hold together until a much higher temperature. Or if they have a really weak dipole or no dipole, then it's really easy to make them roll past each other and be a liquid at a lower temperature. So these are both solid or liquid, but they're pure substances, like Mel was saying. In lab, you saw diagrams kind of like this, right? Where you had like a whole bunch of things that were, either together or apart. If you look at the orange and the blue ones, does this look familiar? So your workshop before lab, we had drawings of a beaker with a little water, and there was different little things. One thing I wanted to make really clear is if we're looking at that, there's one really important component that was missing. What was that? What was the important thing that was missing from those? Water. That little squiggly line at the top said that this is in water. So either it's a solid, right, sitting at the bottom of that water beaker and not going anywhere because it's not dissolving, or water gets in between all those ions and breaks it up. And when you just saw these things kind of scattered around, it's really easy to forget that there's so much more water. So aqueous means this. Liquid means what we just looked at. So if it's aqueous, it means it's surrounded by lots and lots and lots and lots of water. But if it was a solid, if we made a precipitate, right, that cloudy stuff that you saw in your test tubes, it would be sitting here at the bottom, and those would come together and fall out of solution. Does that help a little bit with the liquid versus aqueous versus solid that you're doing in lab?
Okay, repeat what you just said about the precipitate.
So a precipitate means that you took things that were aqueous, that were floating here amongst a whole bunch of water. When they run into each other, they're really attractive. And that means that they push the water out, and now they're heavier than water, and they're going to float to the bottom, or sink to the bottom, and you're going to get a layer of, you can centrifuge it to speed it up, which you did in lab. You'll end up with a solid that sits at the bottom.
Okay.
So if it's up floating around, completely mixed, a heterogeneous mixture, I guess it's a homogeneous mixture. Homogeneous mixture, where everything is kind of equally spread out and really well dissolved, that's aqueous. Lena?
Does it have to have at least 2 hydrogens and 1 oxygen to be aqueous?
So this equation down here has nothing to do with what we're talking about. So no. So a nitrate, sodium nitrate, is very soluble. And it has nothing to do with what's here. I was just trying to get the visual. This magnifying glass is all I want from this slide.
So how could we tell, like on the test, if you asked us if something was like liquid or aqueous?
If it's a pure substance, and it's melted, and it's moving around freely, that's a liquid. If it's not by itself, if it has water all around it, and it's moving around freely, that's aqueous. So, pure substance can be a liquid if it's moving around. And the one that I just closed, where it's not pure, there's a mixture of water and something that are separated, that's aqueous. So you'd have to know...
Like a diagram like this?
So really you need to know this. My point is, I want you to know what this means, right? It's not soluble. What the hell does that mean? Well, it means it's not floating around, it's not separating. Those ions are not, if they're soluble, they're not staying together, they're moving around with water. So for the last 25 minutes of class, we're going to switch gears. And we're going to start working on focal activity. So go ahead, in that packet that I gave you, with the, what's it called? Balancing chemical equations, the carbon cycle. Go ahead and work through Model 1. I want you to try to be as efficient as possible. So let's focus. This is going to be, if we get through this, it's going to be really helpful for lab this week and for the exam. If you get stuck, do not wait too long to ask someone or call one of us over, please.
This will be helpful for you guys next week. Oh, it says in model
Before we wrap it on the thing. So these are the reaction molecules and products. So it is just that simple. It's just that. Okay. Because we're good missing something. Okay.
And then start with the reactants, and you go to properties. Or you react to reactants. Is that helpful? If it's reactive, this product.
Also, I was like, it's gotta be these. And this one was like, it can't be that easy.
It is that easy.
It's just the chemistry.
We do have 3 people I would say for example.
I don't know any.
Those are make sure that you're whatever you have on here.
What are you calculating? Am I calculating the, am I calculating I didn't know if I was just supposed to do this
Yeah.
Hey, don't give me that yourself.
That's what I Make sure you finish up through at least the first table. Actually finish through, where is it? After, I don't have a sheet anymore because I gave them all away. Can I see this? So I want you to finish all the way through Model 1. So we're going to have a group discussion then. If you finish that, then go ahead and start Model 2.
This is a molecule.
That's what I would say.
I don't know about the exact numbers, but
Yeah, I'm just trying to like finish like getting these done, and then I can just type it in. This is only concerning him.
Yeah, this is
Yeah, it's just the because I need 12 o'clock. Right.
I was like, I was gonna get this hard, and I was like, I just can't get this one. Okay, but I'm talking oh, I got out of it. I got this big copies of it straight to Reaction to 4. How many types? How many? All right, so I have a question up here, quicker question. I want to know about this idea of a balanced chemical reaction. Remember the way that we answer these where it's multi-select? So if you think it's 1, 2, and 3, hit 1, 2, 3, send, 123. If you think it's just answer 3, you hit send, 3, send. If you think it's 2 and 3, then do 2, 3, send. Does that make sense? But do it in numeric order. Let's do another 10 or 15 seconds. All right. Go ahead and close that out. So we have a little bit of a mixture, and I'd say the biggest mixture is between saying it's both 1 and 2, or it's only 1. Discussion, what do you think? Morgan?
I think it's 1 and 2, because the mass of the atoms isn't going to change.
So there's a pre-statement to that. So say why you think 1 is appropriate, and then you just describe why 2 is. So describe why 1 is appropriate.
Because the balance, you have to have the same number of atoms on one side as to be the other side.
Okay, so as what you worked on in the packet showed that the number of atoms that you start with are the same as that you end with. And then the second part to that is, well, then Morgan said that the atoms don't change mass from the start to the end. So if we have the same number of atoms in the beginning and the end, then we have the same weight at the beginning and the end. What do y'all think about that?
Yep, I agree.
I agree. So when an equation is balanced, it means that we have the same number of atoms at the beginning and the end, and then the same number of weight before and after. So we're going to do one pre-thing before Model 2, and this is not in any of the material, so you have to look at the screen or at the clicker question I just sent you. What is the molar mass of the molecule methane? And I want you to enter a number and a unit. Molar mass can also be described as molecular weight. All right, it looks like everyone's got this, so we're good, right? Close. Okay. So what does this mean? Let's think about the name. Molar mass. So it's going to be a ratio. And it involves this term, the mole, which we haven't really talked about much yet, right? What is the mole? What is a mole? What is the mole?
Mole, mole, mole.
Ankar?
It's 6.02 times 10 to the 23rd.
It is a number of things. 6.022 times 10 to the 23rd. Is that a lot or a little number of things? It's a lot. If you had this much, even pennies, you'd be richest person on the planet, right? This is a billion, billion, million of them. Why is this number important? Why do we care?
Avogadro's number.
Because Avogadro. Amadeus Avogadro. Important person. So it is called Avogadro's number. But this is how many things are in really a chemist's dozen, if you will. What's a dozen mean? 12. So does a dozen have to be eggs? Can a dozen be students? Can it be cars? Can it be molecules? This is the same exact thing, but this is a number that chemists use a lot because they measured out 12 grams of carbon 12, and they said, how many atoms are in this 12 grams of carbon? This is how many atoms are in 12.00000 grams of carbon 12. So to find the mass of a mole of carbon and 4 hydrogens, how would we find that? What is hydrogen? 1.008 or 1.00794 compared on that periodic table. So, how much does CH4 weigh? 16 point, what is it? Does anyone have a calculator? 0.429. And that's how many grams are in 1 mole. So the number, a mole, is a number that we use because 16 grams, if you're in the lab and you put 16 grams on the scale, can you picture how heavy can you picture how much that would be? That's like something you could weigh, right? You've used the balance a lot this semester. So maybe this pencil weighs about 16 grams. So you can see that. We're not going to be talking about atoms, and we're going to try to visualize things on a scale that we can actually weigh and we can see. So if I have a mole of methane gas, methane molecules, it's going to weigh 16.0429 grams. What about the molecule of, can't remember what I have. Let's do the next one. So what is the molar mass for carbon monoxide? Make sure to include units. So can I get someone to volunteer to talk me through how they're doing this? Sebastian? Can you say it nice and loud? So let's be really careful. AMU is a measurement of mass. Is that a big amount of mass or a small amount of mass? It's really, really little. We use that to describe the weight of atoms. So if I had one molecule, just one C with one O bonded together, I would say that they weigh 12.011 AMU for the carbon, plus 15.999 AMU for oxygen, 9994. So that's the weight of one molecule of CO. What does that come out to? 28.010 AMU per molecule. But what we're going to do is we're going to shift gears. And we're going to say, if I have a mole of them, a mole of CO molecules, it's that many grams for a very, 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 very large number of them. So what you're going to find, and it came out in Activity 2 when we were working through that POGO Activity 2. The number you find at the bottom of the periodic table is either the mass per atom in AMU or the mass in grams of a mole of them. So we have two conversion factors now. If you have 28 grams of carbon monoxide, how much do you have? A mole of it, which is 6.022 times 10 to the 23rd molecules. Let's say I have 14 grams of carbon monoxide. How many moles do I have?
2 moles.
Half a mole. Or 3.011 times 10 to the 23rd molecules of carbon monoxide. So this is now a conversion factor that we can use to go from grams, which is weight, to moles, which is how many, or from moles, which is how many, to grams, which is how heavy. We can do that on the molecular scale, or we can do it on the bigger scale. So this is something that I would really like to have an extra 10 minutes to practice on, but I know people have lab and lives. So for our lab this week, you will be asked to calculate the molar mass and to use that to convert between grams and moles, moles and grams. For the exam, I will probably just ask you to find the molar mass, and you'll need to make sure that you use the appropriate units. You could do conversions between that, right? What can you not have on your note card for the exam? You cannot write polyatomic ions. And I will give you the electronegativity table. I will give you this. I will give you a periodic table. And I will give you the solubility chart. You can put angles on there. You just need to know how to use it. Julia? Finding the molar mass will be on the exam on Wednesday.